following is a conversation with John Lane Bell, a philosopher, mathematician, and logician, professor emeritus of philosophy at the University of Western Ontario in Canada. He has grown academically in Oxford, where he did his Bachelor of in Mathematics, and then subsequently completed his Doctor of Philosophy in Mathematics. In this conversation, we are talking about the philosophy of mathematics, physics, logic, and then the nature of consciousness. I hope you will enjoy this conversation, and this is Back to the Stone Age.
This is a sort of personal history, or short account, actually, not a history, of what I think, or have come to think over the years, about nature of mathematics. Well, in my youth, I was a Platonist, as so many of us were, but I later grew out of it. Took a few years. In particular, for example, in said I no longer believe that there is an objectively determined cardinality for the continuum. In that, I shared views with people who are gone now, like Saul Pfefferman and Andrzej Mostovsky and others who had this view, and Paul Cohen, for that matter. Anyway, I like to joke that Platonism, in mathematics at least, is a sort of mild malady of the mind, which, like measles, should be conceived early in life so as to obtain the necessary immunity for one's older self. I've come to agree with Saunders MacLean, and I suppose Wittgenstein, that pure mathematics is concerned with rule rather than truth. You may call this formalism if you like. Formalism does at least have the merit of offering the weary ex-Platonist a welcome refuge. A mathematical theorem is correct, I believe, that is established by the correct application of rules laid down in advance, as opposed to being true in the usual sense. That's what I now think. Truth requires correspondence with facts. And I don't think there are pure mathematical facts as such, except in the sense of, for example, it is a fact that 2 + 2 = 4 is a theorem. That's not the case for applied mathematics, of course, because applied mathematics is concerned with objective reality. And there certainly are facts about objective reality, which involve mathematical terms such as numbers. Thus, the proposition of applied mathematics, 2 apples plus 4 apples, 2 apples plus 2 apples = 4 apples, is true. But the proposition 2 + 2 = 4, 2 core, is simply correct. Of course, mathematicians and others routinely say the mathematical propositions are true, but only the true Platonist would claim that this means more than mere correctness, that there is a pure mathematical fact making the proposition literally true. I regard mathematical Platonism as a product of a natural effort to supply pure mathematics with an objective subject matter, to enable it to transcend the practice of mere rule following, which, the way it sounds, I said, almost trivializing what many people think about mathematics. And in some sense, I think Platonism, in some sense, is in a way ennobling mathematics. It's just not a bunch of mechanical rule following. According to Platonists. Anyway, the origin of mathematics lies the origin of mathematics lie in its use in applications to the material world. That were very likely that's its origin, at least major part, source of its origin. Arithmetic and counting, geometry and measuring size, which are the 2 major branches, really. In prehistory, there was no pure mathematics, except possibly the use of counting in early religious ritual. At least some historians think that's maybe where the whole business of counting originated in this public sense. I mean, not the practical part of it, but the part that sort of evolved into pure mathematics. It's still debated. But it was found that the practice of mathematics, initially in arithmetic, later in geometry, could be distilled into a number of formal rules, such as the laws of arithmetic or the postulates of geometry, which, when correctly followed, always result in true, or in the case of geometry, nearly true assertions about the real world: 2 apples plus 2 apples, 4 apples, or the sum of the angles in a triangle is equal to 2 right angles, and all these basic geometric propositions. To ancient cultures such as the Egyptians and Babylonians, if there was such a thing as pure mathematics, it was the body of these formal rules. But this changed with the ancient Greeks. The Pythagoreans, who introduced the term mathematics, meaning knowledge, asked themselves, what is mathematical knowledge actually about? They thought that the rules of arithmetic, for example, had to be more than just formal rules, like the rules of a game, but in actuality expressed truths about an actual subject matter. In this case, a realm of objects called numbers. Numbers are not material objects, like apples or stones, to state the obvious, but they are objects nonetheless, and arithmetical propositions express truths about them. Well, at least that was the Pythagorean view, as far as we know. Later, Plato extended this idea to geometry, supplying it with a non-material but objective subject matter of ideal geometric objects such as lines, circles, and spheres. This is the source of Platonism, so-called, in mathematics. Mathematical Platonists such as G.H. Hardy, Gödel, Roger Penrose, and Anna Kohn, probably the most well-known contemporary Platonists, very good mathematician, believe, like Plato and the Pythagoreans, that the purpose of mathematics is to establish truths about an independently existing but non-material realm of objects. For the last century or so, these have been called sets. Now, of course, there's a big argument about, well, set theory had that quite, but there are other developments of mathematics which are attempting to break down the kind of position that set theory has had as a foundation for mathematics. But set theory is very strongly believed by these practitioners as being in some way objective, like numbers. It's not the same as category theory or the more algebraic parts of mathematics that are more algebraically based. Set theory is not algebra. Anyway, we'll come to that later. At one time, I more or less accepted this doctrine. I started in set theory, or at least some years ago. I've since moved on. Finally, I'd like just to say that mathematics may actually be formal in content. I mean, seems to be, as I say, you can call it formalism if you like it. Although Saunders Mac Lane didn't like his position to be called formalism. You can read it in his mathematics form function. Anyway, may be formal in content, but still, I think, must be recognized as a product of human activity in the real world. Like everybody else, mathematicians should accept some responsibility for how their work is used.
Thank you, John, for this introduction. And I would like to, in the light of your introduction, I would like to ask you if, according to you, is mathematics a tool, or as you described it, a set of rules that we use to describe the universe, or is the universe fundamentally mathematical in nature?
Yes, that's a $64,000 question. Right? It's clear that much of at least the contemporary mathematics has become rather more of an art than a science in the same sense as physics or biology and so on. And the reason for this is that I think when we talk about basic mathematics, numbers, or basic part of geometry, I mean, especially the use of geometry, say geometry and physics, the description or the content of the purely mathematical content of the assertions, say in number theory, do have translations, pretty well direct translate, much of them anyway, into actual statements about objective reality. Uh, I don't think crystalline cohomology and areas like that do have such direct application. In fact, I'm inclined to think that the statements about completed infinities don't actually have the direct. Well, I'll come back to that. Uh, that statements about actual infinity and seti, do they really have direct interpretations in the objective world? All right, what is the objective world? Well, not a philosophical question, but I mean, let's say the world of let's take a rather like those cosmology. I mean, these statements like that 2 to the Aleph 0 equals Aleph 23 have any real meaning at all in that world, in the actual world, let's say, of the cosmos. Well, that's an old issue, and the, there are clear differences in the way in areas of mathematics that can be interpreted in some way directly in the physical or material world, and those which probably can't, unless you really think that the cosmos actually does represent, it does have these gigantic infinities in it. Cantor did seem to believe that, at least it's not entirely clear in his case, but that he thought that physics, that actually his set theory, actually, which involves the major innovation that he introduced there really is the use of actual infinity and accepting it as objectively true statements about objectively meaningful. Of course, exactly what he meant by objective is also in dispute. Did he really mean when he say the power of the continuum is such and such? Or there are exactly so many points on a line, or there are exactly so many objects of a certain type in the universe, which is not necessarily countable. Now, so in that case, there's a certain amount of mathematics which is actually, if you like, discovered. But it's discovered once the appropriate definitions and concepts have been introduced. Now, those concepts, of course, probably originated in prehistory with simple notions of numbers or with discrete objects and also with things like shapes and so forth that exist. We can say do have some kind of objective material existence. But the idea that somehow mathematicians try to give the impression, not all of them by any means, but the mathematics is somehow homogeneous. Really, there's no essential difference between one area of mathematics and another in terms of its potential, if you like, in describing the world. What they really have, areas of mathematics that really seem to have in common, I mean, they may have other things in common too, is that it's this idea of correctness. It's the idea that whatever mathematics is about, and that is disputed. The meaning of mathematics and its definition has changed. It used to be the science of magnitude, number and magnitude. That was the traditional definition. Well, of course, what do we mean by that? Well, okay, arithmetic and geometry. Since the Pythagoreans had music and astronomy, and those were thrown out. So we moved on. But I think in the case of it's not clear that the idea of mathematics as being a complete abstract game with formal rules is clearly not correct. On the other hand, the idea that it's somehow if 2 + 2 = 4 makes sense objectively because you can actually illustrate this, taking 2 apples and so on. Then in that case, somehow all of the other types of mathematics must have potentially the same possibility of having a reference of that sort. And I don't think that's the case. G.H. Hardy, very interesting, of course, the people who are really Platonists in a matter like Hardy. Hardy thought mathematics was objective, but he, as I said, he's a Platonist, and he thought it wasn't about the actual, it's about an ideal world. But the thing is, the connection, the interesting thing is, it's perfectly consistent to say it's about an ideal world. You may or may not believe it. It's like the existence of God. I don't think the existence of God is an absurdity. I don't happen to believe in God myself. I don't find it nonsensical. On the contrary, it's obviously a proposition that would have some content, right? But in the case of something, in the case of a Platonist like Hardy, he didn't think mathematics. He thought mathematics was pure mathematics, in the sense that some of it might have application, but it doesn't necessarily have that. It didn't. It may have arisen for that through simple applications in prehistory. But what's actually happened to it is it's simply taken off and become a self-sufficient area or study that has detached itself really from application. That was his view, and it's fundamentally, I think, in one way or another, the view of most Platonists and people, mathematicians, who this notion that mathematics is if you like, a pure art, and I think that it's as you say, well, it's a point of view, and obviously it's a question. But of course, once mathematics detached itself, you see, from its applications, or at some point, then of course that question arises as to why parts of mathematics that weren't actually originally devised, if you like, that you can't do them directly from experience, or through the senses, if you like, directly. Well, how is it that they actually work? The good old Wigner question about the unreasonable effectiveness of mathematics, right? Which is still a good question, and it's not very easy to answer. It certainly isn't easy to answer if you think of mathematics as being something completely homogeneous. Then you're really confronted with this problem. If you see, I don't know if you've ever seen, you possibly, but if you haven't, you should. These arguments that Alain Kohn, is a great contemporary mathematician, who's an extreme Platonist, brilliant extreme Platonist, had with this neurophysiologist, this Changeux, and he did these debates with them. And as part of it, Changeux thought it's all material. Basically, it's in the mind, mathematics, but it's basically a product of the brain. It's not really about anything that really exists independently of the brain. That's Changeux's view. It's certainly not Alain Kohn's view. Yet they've published a couple of books or conversations on their part, agreeing, so to speak, to disagree on this question. But it's actually very difficult to answer. And it's particularly difficult to answer if you think of mathematics as just being one sort of homogeneous thing, a kind of either or. Then, of course, then one of your original questions is whether mathematics is invented or discovered. Well, again, that's not so. I tell you, I think it is a connection. I hope I'm not going too far off the point. I think that in the case of this discovery, I think that mathematical concepts have been invented, yes, but language was invented. I mean, that's another problem. Language doesn't just come out of the sky. Presumably it appeared, although it's a deep puzzle as to how it emerged. I say, evolution explains it all. Well, of course it doesn't. It provides conditions under which, I guess, language and mathematics and so forth can actually emerge. But it really doesn't explain, and it's not required to explain the particular forms that they take, or how and why there's this diversity of language and so forth. Interestingly, there's not much diversity in mathematical. Of course, in language, of course, it's more the merrier. In mathematics, and that's true. That's another reason why people seem to think, well, they do think, that mathematics is homogeneous. The mathematics of the Babylonians, the mathematics of the Greeks, it's all really the same. And to some extent, that's true. Certainly, you've got to, by comparative language, you've got to go much deeper, as Chomsky showed, in language to explain how it is that these divergences like to follow, or what philology was doing, 100 years before, to find the common, to make language look homogeneous, because it doesn't look homogeneous, at least on the surface. Maybe you don't have to go that far into it to see that you actually have grammatical. But that's mainly in terms of grammar, the grammatical part of it. And in the case of languages, there's a sort of arbitrariness, of course, to the way that languages actually function, or at least the terms that are used, whereas that's not true in mathematics. And that is another interesting thing about mathematics. That of course, it is a language. It uses it has that in common with language. It has, well, particularly symbols of linguistic devices, really. But otherwise, I think finally, I think mathematics is invented. But if you take a problem, so when you say, I've discovered that 2 + 2 = 4 is a very good example. It's so simple, right? That once, so let me give you an example. Let's take an area, let's say, of abstract algebra. What became abstract, I'll say the group theory or whatever you like, group theory. The notion of a group as a concept, before Galois sort of intuited it, he didn't formulate it specifically. Did it really exist? Well, I like Paul will say that all this stuff existed at the time of the Big Bang. Right? It doesn't seem very plausible to me, right? We like say, oh, well, the statue of David, and Michelangelo's David, well, in that block of marble or whatever it was that Michelangelo was using, somehow the statue already existed. Well, of course, that's another potentially, and that's how the philosophers get around that problem. Oh, yes, potentially. Yeah, potentially anything. And if you're right. But anyway, finally, I think that it's initially what you have a concept, say group theory. Then that concept crystallizes. And then you say, well, the notion of a group was invented by us. It's true, it does have examples in the world, not maybe as straightforward as the numbers, small discrete things. Then you say, oh, but then it becomes legitimate to say, oh, well, I haven't discovered it was invented. So once the concept is put in place, then it becomes a discovery that there are only so many finite, and so forth. But others, you could think of mathematics as being a lock. It's like a lock that builds, it could use as a lock and then has a problem finding a way of opening it. It's the discovery, then you can open it, or you fashion a key that does it. But the point is there are constraints on that are determined by previous concepts that actually have a particular, that were invented. I mean, they in some sense they didn't exist before, at least, and I think that's of course particularly true with it's the area where this really where in the case of arithmetic and geometry they were both tied initially, right, to, if you like, to notions that could be understood almost directly, but it could be presented to the senses directly. I don't think that's true. Well, maybe a group theory, you say, yes, you have composition of operations and so on. But the point is that I think those concepts have, it's the same with arithmetic, or those concepts are invented. Arithmetic, but you never say in arithmetic, for example, people say, oh, I've discovered that every even number is the sum of, well, proved it. Of course, the idea of discovery has to be backed up. The invention of the concept doesn't have to be backed up. There's a difference once you introduce a concept. Anyway, so the analogy of a lock and a key, I think, is helpful there, simply because you can see that you might say, oh, well, somebody has actually produced this lock. Erdős would say, oh, God did it. It's Erdős's notion of the book, book of numbers that he had. Oh, the answer is there. We just haven't got to the right page yet, And yes, and then, but once that is established, that book or lock or whatever, then it would be a discovery that you can open it or deal with it and so. Because it
there is a
known.
mixture. There is a mixture of both invention and discovery. That's what you're.
That's right.
Saying.
Okay. Invention, discovery, they're very close. In mathematics, because in line in other areas, for example, you don't have exactly the same problem. Did Coleridge discover Xanadu? Xanadu, did Kubla Khan a stately pleasure dome decree where out the sacred river ran through caverns measureless to man down to a sunless sea? Or did Shakespeare, shall I compare thee to a summer day? Was that discovered? We don't have that difficulty. Well, of course, the term discover, Italian, I can't remember the Italian languages differ, of course, in their. In some languages, I would presume the notion of invention discovery are maybe closer than they are in English. But in mathematics, it's very much it's an important question in the philosophy of mathematics, whereas it's not such an important question in linguistics. Okay.
Could it be that the sort of discussion and debates or doubts that we have over philosophical questions about mathematics, as whether mathematics is invented or discovered, might be the reason, might be due to limitations of our language and sort of, limitations that our language intrinsically has in meaning and expression.
It's a good point. You could push. When the language of interest, of course, in the case of linguistics, you have a language study generally, the two aspects of syntax, right, and semantics. You can split those up. Of course, they're connected. The syntax doesn't really explain the semantics, how you get reference at all. But in the case of language, you do have a reasonably clear, that there are parts of language that are just there for syntactical reasons in order to make the proposition, express certain sorts of ideas and propositions. That, this or that, or let's say, that's a bad example because this that is over there. There, of course, but the particle, and then the ones that the logicians have taken, the ones and or. Right? It's remarkable that those statements or the logical connectives are not. They're important in language, but don't be all and end all by any means. There's so many, and or not. You could do a propositional logic completely. Those notions and some combinatorial things where you construct statements of them. There's nothing like that. Language is much more complex than that, and the reference and the idea of reference is much more difficult. And the idea that you have in language, the notion of what one actually discovers in the case, right? Oh, I've discovered that I can use the term such and such, to mean such something else. You might have a situation like that. But in the case of mathematics, the difference between discovery and invention is something that is much clearer, right, in a way, than it is in the case of language, because you have the whole the language does refer to abstract notions that don't have direct material, of course. But and then there have been arguments about that. Did Sherlock Holmes, in the case of language, nobody has a problem about it saying, well, did Sherlock Holmes really exist? No, since you actually have a record directly, you like Doyle inventing the character. In mathematics, you ask a similar question, you end up with doctrines like fictionalism and so on, which I find rather attractive in a way. It's like I like literature, but they don't seem to make the same. They're not nearly as clear cut. So when you say, numbers don't really exist, they're just symbolic conveniences. Richard Russell used to call them. But in the case of language, it's a similar thing. It's rather clear, at least in everyday use of it, whether something actually is a referring term. Sherlock Holmes is not a referring to. Refers to a character want to call them stories or Sherlock Holmes stories. But the term the sun, no, that is a referring term to something objective, which would be there whether we actually, whether we'd invented a term for it or not, or at least that's the usual view. Now, in mathematics, it isn't so clear. Right? It's because there are very few mathematical terms which do have direct reference, unless you supply them, well, by set theory or by some Platonistic construction. And that's, of course, an amazing thing that's been done, because I don't think there's any other area where, in a way, the whole reference of mathematics, I think it's been invented, but on the other hand, mathematics is the invention under considerable and systematic constraints in a way that isn't the case in
Okay.
painting.
I like the description of invention under constraints. I do.
Yeah.
I came to sort of agree with one of my previous guests that mathematics, or let's say that in mathematics we invent the axioms and we discover their consequences in
Yes.
trying to find out about any specific mathematical reality. I would like to ask you now, what is mathematical constructivism and what are the differences with Platonism?
Well, I give you I'm going to get preface my remark on that with a little bit of again, with a little personal history. I sort of met in logic long ago, back in the 1960s, and I didn't come from. Actually, I wasn't going to be a logician. I was originally going to work in functional analysis. I was mathematician. I was a physicist by origin, but we won't go into that. And I had no idea about. I mean, I'd heard that there was an area where the law of excluded middle was denied. 17 or 18 or something extremely strange. What does it actually mean? Well, later on, and I'd read and I knew more or less what constructive reasoning was, I mean, at least for me, but I couldn't really see that it didn't seem to be terribly interesting at that point. That helps a Platonist. Then, in the case of once, if you look at the original source, later after I got really interested in constructive mathematics, it wasn't so much you find that there are two sort of, one is the source of mathematics as if you like, as methods of calculation, which has been around an awful long time. I mean, long before, even before, let's say, Kronecker, and then right in the 19th century, this idea was, well, God made the integers, and man, and all the rest is due to man, sort of stuff. But the idea that mathematics is concerned with things which could be presented as I say, as correct, and you could show, right, how you actually produce these. In other words, there's an epistemological element. See, the main difference, I think, at least, or one of the principal differences between constructive and let's call it non-constructive, well, constructive mathematics and mathematics in the old sort of, where you didn't use the term when the term constructive wasn't used, is in the case of the pure mathematics, there's not much of an epistemological element in it. It doesn't, of course, you then have to go to psychology in order to understand how it is that mathematical propositions are understood, or you develop an idea of a proof, you may have this idea of correctness. But the logical element of how we know that a mathematical proposition is correct or true, whatever your orientation is on that, is not included in the proposition. 2 + 2 = 4. Well, implicitly in the case arithmetic proposition is very close. I mean, the case of elementary arithmetic is a good example. The distance between the actual establishing of the truth of a statement. In arithmetic, it's very close, quite close to the actual statement itself. Of course, when you have large numbers, then I've got a nice example of that maybe later. But the distance isn't all that great. Now, when you become in why it is that a mathematical proposition is correct, then you get the constructive element. It's not there simply directly in mathematical texts. You read them, certainly classical ones, but they don't tell you how it is that given, theorem proof. And of course, it's true, you do have rules for yes, although they're usually not given in the text. But the point is that in a constructive statement, or when the idea of verifying it's true, it's a kind of verification, notion of verification. You often wonder, well, how do I know all this? In the case of mathematics, particularly complex mathematics, where you have proofs that are 200 pages long. Look at the proof. Look at the, I don't understand it. Proof of Fermat's theorem, Wiles gave, whatever it was, 30 years ago. 200 pages. The Fermat's theorem itself, all this does, you can state in the New York Times, they did, Fermat's theorem. There it is. And yet it takes 200. What's the content of it? Well, officially it's just about numbers, but actually, in terms of the understanding of how the truth or the acceptability of the proposition is arrived at, not included in constructive mathematics, it's brought out explicitly. That's the difference. And in the case of the constructive mathematics in the past, well, there were two forms of it: computation and arithmetic, which is probably the earlier. And then in the case of geometry, it's interesting because a geometric, the term construction is one you learn at school that you're used to. For geometry, you never heard about construction. The term construction and was Euclidean geometry. It's how you cut the sphere, a circle in half, or you do some arguments. And most of the arguments in Euclidean geometry, although they're given, of course, in terms of theorem and proof and logical deduction, many of them involve things that are called constructions. And most of, I don't know whether they teach geometry in schools now, but certainly I remember when we learned it, I don't know, long ago, that's where you understood the term construction, because you understood how it was that a proposition, right? How the proposition became accepted as correct. And in constructive mathematics, that has to be implicit, or it may not be completely explicit, but it's part of the meaning of the proposition. In the case of a proposition, simply a proposition in pure mathematics or this classical mathematics, that's not included. Oh, of course, you might say, oh, yes, a great example of that, of course, is Ramanujan. I mean, who knows how he came across his extraordinary. Now, really, again, when it's just written out, you see these things, extraordinary formulas. How did he get it? But the point is there, that's not part of the meaning of the proposition. In the case of constructive mathematics, it's built in there somehow. That's the difference. And of course, that makes it somewhat, it's two practices of mathematics. The Brouwer had the idea that somehow, of course, he was a monist. Most of these people are. There really is only one true mathematics. And in his case, it wasn't really constructive directly in the sense of Bishop or later, Plato or natural analysis. It's really direct intuition. Right? So constructive, it's interesting how that's all got mixed up, because intuitionism is not constructive in that sense. It's constructive in the same way in a Kantian sense, that you perform mental constructions in order to get mathematical results. And for Brouwer, that was what he called it intuitionism or neo-intuitionism. And then, of course, what happens is you get a different type of mathematics. Oh, they overlap. But as I said, the main difference is the mathematics just asserts what you might call truth. Okay, that's why the Platonist thing is then easier to understand. It just asserts truth. It doesn't really make any. You can get it by divine revelation. Yeah, it suddenly show up like angels. Oh, finally, the scales have fallen from my eyes, and I actually see. Oh, of course, it might be back. Then if it's backed up by proof. Well, look, constructive mathematicians have intuitions too, but the point is that the criterion for actually accepting them as part of practice involves an epistemological element. Mathematicians, of course, do have the constructive aspect of pure mathematicians is called proof. And the argument will then be about what are the acceptable proof methods. You can't just come along and say, oh, I divine. Ramanujan almost, he got away with it. He didn't seem to understand proofs. I did proof very well. And it's psychologically, it's very difficult to explain how he did his but anyway, that's the principal difference. And then, of course, what will be accepted as correct from a logical point of view then get modified. Bauer himself wasn't terribly interested in logic, as you may know, but it's true that he did think that it was the law of excluded middle. To the extent that he wasn't, he said, well, that's the sin of the Platonists. And it's true.
Okay.
It's obvious why the law. If you say a proposition can only be asserted when it's known to be true, then the excluded middle is bound to fail.
Okay. What are the philosophical implications of adopting a constructivist approach to mathematics? So, in rejecting the law of the excluded middle when
Yes,
we
I
are
think
dealing
that
with
is the prime. Yeah, I think
intuitionist
that's the primary
logic.
thing. And well, I mean, look at the argument between Hilbert and Bauer. I mean, Hilbert understood constructive. He didn't like it, and there were historical reasons why he didn't like it because of 19.
Why not?
Oh, because of course Hilbert's original work, of course, early work was proving things by I mean he freely used the law of excluded middle or the idea of saying something exists without showing how to get it. His proof of Waring, so there are various things in number theory, for example, Waring's theorem about how you express numbers in terms of sums of powers, and showing that every number in principle, for any power, you can show that there's. I can't remember the details now exactly, but that for instance that every number can be Lagrange's theorem. Every number is the sum of most four squares and so forth. So for cubes it'll be 9, I think. But then what Hilbert proved in whatever it was, and sometime towards the end of the 19th century, was that for any power, you'll be able to show, or that it's that any number can be expressed as sum of so many numbers, which are each of which has that particular power. So he didn't show how to do it. He did it by the usual laws, the ordinary classical logic, which didn't come into question. But the point is that he didn't show. He gave no method of calculating what the number is. So how many 27th powers, for example? What's the bound that you could place, say, on expressing numbers as sum of 27th powers? Well, Hilbert showed that you could not that you could do it, but there was such a number. And he argued by contradiction. He said, suppose there wasn't one. And then got a contradiction, the actual form of the reductio ad absurdum argument. And then in that case, and then he converted the statement that there isn't such a number bound leads to a contradiction. Therefore, no, there must be such a number. Yeah, but it doesn't prove. That was objected to by lots of. I think it wasn't in that exact case, but when response to some of Hilbert's proofs was, this is not mathematics, this is theology. I mean, namely that you prove something, that if something exists, say a number of a certain, and you the way you get it is assume it doesn't exist. Then you get a contradiction, therefore it must exist. That's how do you get at it? Now, of course, that's a perfectly acceptable procedure in classical mathematics. And Hilbert wanted to defend it, but he could see that of course, that it's not the same as actually computing what that value is. But classical mathematics doesn't require you to have to do that. But Bauer thought that it did require, or at least you had to perform. Right, so you had to produce evidence, right? Direct evidence. Well, you could say, yes, I have evidence for the proof, right? That there's, well, suppose you say you get a contradiction from the statement that every even number is not the sum of two primes, and then therefore you convert it. Well, that's classical evidence, but classical evidence for truth of or acceptability of a proposition is just a lot weaker because it doesn't require you to say, oh, well, Weil, I'm just talking about him. I wrote a lot about Weil. Uh, that they're just like, what did Weil say? Well, what term did he use for it? Well, mathematics, it uses the non-constructive law of excluded middle, or it wasn't so. It was a consequence of the law of excluded middle, right? That the negation, right, of a universal state is an existential state. That is the real key.
Okay.
You want to show that there exists something, and you do that by saying that it doesn't exist and nothing's satisfied. You get a contradiction, and that was the real use. It wasn't so much the law of excluded middle directly, but it was derived from. It was the idea of proving existence statements. I mean, and that was
Okay.
not it. And the point of the Brouwer thought, for Brouwer, it was obvious that one because he's thinking of mental, as intuitions, where and given directly an intuition. Well, of course, that's a major Western philosophy, and that's how it originated. And you get a different practice. Actually, you get a subtler practice.
And you have been an advocate for this approach.
I mean, intuitionistic logic, which is the term is rather unfortunate. Historically, it came, of course, from neo-intuitionist Kant, really. No, it should be. I used to call it my elementary, undergraduate courses. I was one of the early started teaching intuitionistic logic to undergraduates quite a long time ago. I think intuitionism. I just called it evidential logic. You have to give evidence. They liked it because the philosophy departments, most of the students who come to do laws, they want to become lawyers. And I was able to give judicial examples of all this. They do logic, sort of very smart kids. Anyway, smart enough not to go into academia. And and they found that they could do very well in better on the law the law exams, right? If they'd studied logic. So I started using exam too. If you require evidence to back up, right, an assertion of a certain kind. In other words, it's just being show me. Right? I mean, you assert this, okay, and you are proving it. But if you don't accept all the rules, as intuitionists don't, then that doesn't. It no longer provides evidence. But basically, the constructive view is that you have to mathematical assertions involve in some way. They're bound of showing the proof, and indeed, then that's why you get the idea that mathematics interpret the constructive interpretation, or the later that a mathematical proposition, to assert it really is to assert it has a proof. And then that opens up more cans of worms, because where are these proofs? Right? But yeah, that's the main difference.
And what is the nature? What is the nature of mathematical truth within what you call evidential logic? So intuitionistic logic.
It doesn't know. There are rules. I mean, there have been many interpretations. The earliest ones, Kolmogorov, for example, back in when was it? Probably about 1930. Produce a logic of problems. I mean, he's a very nice way of interpreting, which has become standard, or it's been absorbed into subsequent formulations of what it means, what, if you like, evidence means in the case of constructive interpretation. It's interesting that they all give more or less the same results. They all more or less give versions of intuitionistic logic, basically, where classical logic without the law of excluded middle, roughly. I mean, there are a lot more subtleties to it. But the idea, where does the truth? No, for example, Kolmogorov's logic of problems. You think of mathematical propositions as problems to be solved in some way, and you lay down rules for what it means to be able to solve a problem, and according to the very more complex statements. In the case of elementary statements, say with arithmetic statements, it would be just verifying by computation. Say their equality statement. One expression involving number 2 plus 2 equals 4. Okay, that again. 2 plus 2 on one side, 4 on the other, right? And you verify. You end up with 1, 2, 3, 4 equals 1, 2, 3, 4. Right? I mean, there's a very simple example of that. And then with more complicated, so that's a problem. Show that 2 plus 2 equals 4. Okay. Simple computation. Then if you have show that 2 plus 2 equals 4, the statement 2 plus 2 equals 4, and 7 plus 6 equals 3, and, okay, and you explain what it means to solve that problem. Then you explain what it means to solve a disjunction problem, where you have a show that's either the case that such and such or such and such. Then negation, which goes rather subtle one, much subtler in intuitionistic logic, classical, because classical is Boolean. It's just, and then in the case of quantifier is just doing that similarly. So, but that's an interpretation of one interpretation of constructive reasoning, which was created by Kolmogorov in 1930. There are others. Now they're the one, of course, that the ones that have actually come from category theory and from topology. And the reason for this is that it turned out that intuitionistic logic, or as it when it was the standard form of it, of course, came from fighting. It was Bauer's pupil back in the 30s, and it's turned out that there are many ways of interpreting it. I mean, but the statements construed to get justifying the laws of intuitionistic law, and what you find is that all of those justifications in terms of understanding what it means to solve a problem, whether it's Clady's realizability in terms of basically number theoretic interpretation, the topological interpretation using open sets, right, as your model of propositions, which was created by Tarski in the 1930s. All of these, not all of them have really embody the constructive element directly. The point is they realize the same rules as the original notion of constructive, which means providing evidence. The interesting thing is that when you insist on having evidence, all the idea can be absorbed simply into the logical rules. That's very remarkable. Bauer, of course, thought that the classical rules were just wrong. So wrong in what? Well, because he thought he's an idealist. I mean, he thought they were really about mental evidence. You're a mathematician. I didn't think they were about mental evidence. Platonist, he thought is actually the same thing as biology or physics in that sense. And the things are there; they're just facts. And our duty is our job. This is the view that I used to call in set theory anyway. The George Mallory view. So when asked, I remember why do these set theories, for example, who are not constructive, and why should they be? They've got their own practice, which was general practice in the past. It's not anymore. There's a pluralism now, I think, in mathematics that there wasn't. Anyway, why is it that the case, let's say, of the continuum hypothesis, it's either true or false, and it doesn't matter whether how we discover it. I mean, in practice, it matters, of course. And that's just more or less the view of the mountaineer. I mean, when George Mallory in the 1920s was asked, "Why do you climb Everest?" He died, apparently. And he said, "Because it is there. Everest is just there. We attempt to climb it." This is the view, Plato's view, and nothing to do with construction. Construction practice, to get to it and do the climbing, you need the thing. funny, even if you didn't climb it, it would still be there. And that is the difference between the construct. If there isn't an idea of a construct, propositions in constructive mathematics don't really have any meaning unless, in principle, there's some way of verifying, or it's in the content, right? Whereas, of course, I've had lots of argument with people, with students on this question, because it's true that the intuitive idea about mathematical problems, oh, well, we don't matter. Statements about numbers, especially about numbers. Yeah, well, they're just true or false. Well, you could understand that. But in the case of the idea of extending to, in the case of arithmetic, there's not a great deal of difference between the Platonist interpretation, the classical assertions about numbers, and the ones that are. There is a difference. What I like best is the fact that classically the natural numbers are well ordered. Right? You know, every set of natural numbers has at least a non-empty set has the least element. That's not correct in constructive. On the other hand, the induction principle, which is, of course, the basis how numbers really are defined, sort of axiomatically, is, of course, correct in both, if you like, both systems. But when you get to different types of mathematics, not number theory, the divergence really begins to appear and becomes much more interesting, I think. At least I came to that view after. Well, I started math pretty early, but I was a very late starter in constructive mathematics. You know, the real diversion becomes at the level of the continuum. Really, then you get amazing because constructively, or it's consistent with intuitionistic logic that every function on the real numbers is continuous. I mean, we know it isn't in the case of classical. It's obviously false. You have a thing called the blip function. You know, zero at everywhere apart from zero, and one at every real number that's not zero, but zero there. Well, obviously, it's continuous. And that's just not a well-defined function. Because you see, Leibniz didn't know. Oh well, get off the. But that's the difference. There you get real divergences, and that's when it becomes interesting, at least to me, because it opens up new possibilities, which is not there in the classical. You can have
definitely
completely continuous world. For example, that's what the smooth topos does. I mean, in topos theory, Bauer himself tried to prove and well establish, if you like, that the real continuum, the continuum he was working with, every function on it is continuous, and he did prove the continuity theorem in 19. Now, of course, the classical mathematicians aren't going to accept it, but they could understand what he was saying. They say, yes, that's your continuum. It's not the real. Bauer was saying, yes, that would say the same thing, except the meaning's reversed. So so in other words, there do seem to be different universes, of course, in the case of classical and constructive mathematics. It's only those who really were monists, like Bauer. See, if you're not a monist, he had to believe in what he was doing, and that meant just stop saying, we got all these other possibilities. This is the truth, this sort of mosaic idea. And he was very much. Hilbert wasn't like at all. Hilbert didn't like the idea of being told what to do. But you see what I mean? That there's a thing now. I think more mathematicians, ones who are interested in these sort of questions, but like most physicists aren't much interested in philosophy, as you know. Most mathematicians aren't terribly interested either. Okay, but for those who are, probably a number, come to the view and become sort of pluralist. There is a constructive mathematics. There's a classical mathematics. There's all kinds of varieties of things in between, right? And then the interesting thing is an interesting aspect of it is to try to understand what you call mathematics. Then becomes broadened. It has to include it's a house with many mansions. That's not the view, of course, of Bauer or of most classical mathematicians. I mean, the ones who are in practice proving, I don't know, Terry Tao, for example, he's the usual, but he's an amazing genius. He's not that young anymore. He's 40 now, but you can see the difference between between classical and say, well, constructive mathematics does, on the whole, require, if you like, it has standards. It's not quite the way of putting it, but the criteria for acceptability of a statement are much tighter. But then a classical mathematician can perfectly well recognize it. It just says, well, I don't practice that kind of mathematics. And where it's become especially important now, of course, is in compute stuff with computers. The underlying logic of computers is constructive, of course. It's rather obvious because you use programs. And you don't talk about, does a program exist? You have to produce it. Of course, it's true that they use metaprogram, yeah, but even so. Whereas when Bar wasn't thinking about it, it's amazing that it's turned out that the computer logic essentially, well, there are various forms, but it's constructed in one way or another, simply because you have the notion of the idea of being recursive and involved computation. It means when you say a program exists, you could show that a program wouldn't exist. You see, right? It's all the ability to halting problem. The work that Gödel and Turing did in the 1930s, that showing that such and such a computational procedure couldn't exist. For example, deciding whether a function is completely well defined, on natural numbers and so on. So it's total. But when you want to say that there is a program, right? These objects have to be produced. It doesn't really mean much to say that there is a program without producing it or giving a method for writing it. What does it mean? Well, a classical mathematician would simply say, well, yes, it's the same, because they think about, it's in the case of numbers, when you say a number exists, whether you can produce it now is irrelevant, as long as you can prove that it's according to your criteria. Computer science doesn't work that way. Look, I'm not a big fan of computer science, especially. I went to philosophy department for years in mathematics. All the other guys, very, very brilliant people, marched off into computer science. I learned this. Not for me, but it is interesting that the computer science is providing in bottom every time we don't see it. Okay, when you see a pocket calculator or whatever, an iPad, you don't actually see what's going on there. But in fact, these are bottom of programs in one way or another that have been explicitly. It's true they've gotten so clever now that we don't produce them directly, but in principle they could be produced. Whereas there's no requirement of that kind in pure mathematics, even though it's consistent. But that's the main difference. One thing that in the case of arithmetic, you won't notice much difference between the constructive view and the classical. There is some. It's when I say you get to the notion of continuity, the idea that every function can be continuous. Well, it's quite radical. Or that you can't split a continuum up. Of course, the continuum is supposed to be connected, because the classical topological thing that you can't split. They say space that's connected, it can't be split into two disjoint open sets or closed sets. But in the continuum, for example, the one that was first proved in classical, the Heine-Borel theorem, is it? No, that's compactness. But anyway, it's a well-known thing in classical analysis. But the constructive case, Bauer, you can't actually split continuum at all into two disjoint pieces, whether they're open or closed or anything else. Those are non-empty. That's a theorem. Bauer wanted to prove this, but there are plenty of ways of understanding that, and that's not consistent with classical logic. If the continuum can be split can't be split if it's indecomposable, cohesive. It can't be split in any way, right? It's two disjoint parts. Lose something, so to speak, in the middle. Then that implies it's a simple exercise. You can then prove you can then prove it isn't the negation of the law of excluded middle. It's the negation of quantified statements. And that means that produces a completely different pie. It means you were living in a completely different universe where everything is smooth. In other
Okay.
words, it's like universal classical physics. You see, that's the interesting thing. It's not quantum theory. I would say no, the universal classical physics, the universal Euler, where everything was smooth. You look at all the classical mathematics and eventually the calculus. It's all done in smooth universe. And infinitesimals also fit in there. They don't fit. They do, of course. There's a wonderful theory of Abraham Robinson's, non-standard analysis. I did know him not very well when non-standard analysis first appeared, when he invented it in 1960. Invented, did he discover it? No, that's a good example. Although it's true that there's a way you could say he discovered that you could make infinitesimal analysis consistent. Yes, that was a discovery. But he invented the system that did it.
Okay.
Yeah,
John,
okay.
within classical mathematics, there is an axiom which allows for the creation of mathematical objects in a non-constructive way. That axiom is the axiom of choice, which has stem out of controversy,
My favorite.
we might say.
Definitely
And
my action of choice.
and I would like to ask you if you can briefly
This,
explain what is the axiom
yes,
of choice, and how is it,
I've been talking
let's
about
say,
the actual. Yeah, the actual choice is the most interesting, probably the most. I don't know if you pointed out, but Frankel and Bargel and Levy, they wrote. Well, there's a bunch of foundation of set theory, but in Abraham Frankel, for example, the Melo-Frankel set theory, did remark once that the axiom of choice is it's the second most discussed axiom in mathematics. Of course, the first one is Euclid's fifth postulate, the parallel postulate. It's not called it's not an axiom. Right? It's a postulate because the axioms for Euclidean in geometry are actually more logical axioms, or axioms of principle. Is the axiom of choice. It should really be. It's interesting because I discussed it in one of my books, the axiom of choice. I don't know if you've seen it. Long book. Axiom of choice fascinated me long before I knew anything about logic. It's important in mathematics, in classical mathematics. It's very important. Now, it was called axiom because when Zermelo first introduced it explicitly, he called it the axiom of selection. He introduced it in 1904. Well, explicitly, it had been used. He recognized that the axiom of choice. What was it? Okay. The simplest way is combinatorial. You say you have a bunch of sets, and the simplest thing is to regard these sets as disjoint, although it doesn't really matter, but it's easier to understand and why one would accept it as a correct principle. Sets. So you think of sets, let's say, as discrete collections of things, whatever they are. It doesn't matter. Don't put any constraint on them. They don't have to be finite. They could just be arbitrary. After all, Newton himself accepted the idea of infinitely many stars. In Newtonian cosmology, there was an actual infinite. The universe, because otherwise you get gravitational pumping. It's an old issue in physics. But anyway, so you just imagine, put aside the question about whether you can actually have actually infinite collection, right? In other words, of course, you can have them and say, well, I can actually enumerate, physically enumerate them. Put all that aside. Okay. Then you get the idea of essentially Cantor's view, that you can talk about collections of individual distinct things, whatever they are. And they could be finite or infinite. Once the notion of infinity, and even you don't even need a definition of infinity. You just use the idea that it just never ends if you try. But if you actually tried to enumerate it, okay. If you have then a bunch of, it would seem reasonable. If you have, if that's your notion, then if you have a bunch of these, call them sets, classes, of course, is what Russell would call them, anyway, sets, and you have a collection of them. So it's not individuals you had now. The individuals, you actually have a collection of collections, right? Collection of sets. Imagine them as being in grab bags, no matter how many there are. And each of them has something, each of the bags has something in it, not empty. Then, that's the case. You see, there's this choice. There are two ways of putting it. You could say then, the natural way of putting it would be then, in principle, you could select one object from each of these bags. Now, of course, the question, what do you mean by selection? The easiest way to say it is to say, well, then there's another collection. Just describe the collection you would get if you could select one from each bag and put it in another bag. Never mind how it was selected. Just say that bag it has exactly one object in common with each of the other bags. Or that's the axiom of choice. That there always is such a selector, right? Now, is it combinatorially, obviously correct in some sense for the idea of a discrete collection? In the finite case, it's rather obvious. You call them, but in that case, you can select. You don't have to say how. That's why I call them grab bags, right? You just go along blindly and pick one out of each of the bags. Here, kid, and then you put them in another bag. Fortunately, when you get to the infinite case, then the problem there is it's not so much the problem of whether the axiom of choice or they call it choice, but call it the selection, the transfer, there are various terms for it, but that there would be such a set. It seems implicit, right, in the idea that you have a collection of these things. Then what you do, another way of thinking of it, start to shrink the number of objects in each bag. And each one, of course, it's true, but you're in for a penny, in for a pound. You've already accepted the idea you have an actual infinity. The question is, what can you do with it? Right? You could deny the whole of infinity and then never have it. If you don't, then you say, well, combinatorial, I can imagine throwing out, right, from each bag, everything except one object in it. And then what am I left with? Well, I'm left with one object, and I put those into another bag. Well, that's the axiom. Of course, it doesn't tell you how you do that. It's irrelevant. That was the problem when Zermelo introduced that idea, which it was implicit actually apparently in earlier mathematics. It was taken for granted, before set theory really managed to sort of get a grip of mathematics. That sort of idea does show up in 19th century mathematics already. Was it the case but when you make it explicit, right? There are two ways you could do that. And they were thought to be the same. They aren't. It turns out they're different. And that's where constructive implications. And that's why, hence, then you said it's non-constructive. Okay, I'm trying to explain why the axiom of choice is not constructive in that sense. It's also constructive, by the way. That's another puzzle. Anyway, I'll come to that. There are two ways you can decide that a choice is made. Well, how can you make infinitely many choices? Well, you can't. I mean, if you're thinking in terms of, maybe you have some idealized agent, as the infinite God, one of God's angels, but in practice, what that would mean is, as Russell put it, there's a famous example of his. He called it the multiplicative axiom, Russell, and it's the multiplicative axiom in Russell and White. And why? Because they'd shown, it was known. Russell himself, I think, proved it anyway. It was known, well, even before that, that it's equivalent. Really, the axiom of choice is needed in order to be able to define what you mean. Well, not what you mean, but to show that if you take a bunch of cardinal numbers and each of them is not zero, then the product of them isn't zero. well, that's equivalent to the axiom of choice if you put it in the right sense. He called it the multiplicative. But the way that and that is interesting because that form of it doesn't involve selections directly. It's all. We all know that if you take two non-zero natural numbers or finitely many natural numbers and they're all non-zero, then their product isn't zero. Well, extending that principle, right, to infinite cardinals, if you define them in the right way, that's equivalent to the axiom of choice. Either there was a confusion, not exactly a confusion, but sort of ambiguity, if you like, in what the meaning of choice was. When Zermelo did put the term that in terms of the idea of making a choice of these elements that you got from each set, right? Then that raised the question of how you would define it. You see, it's one thing to say, see, again, that's why it was called non-constructive. Constructive would mean, well, you tell me, you give me if you like, a procedure for selecting one object from each of these. I mean, if they're infinite, Russell put it the following way with the shoes and socks. And you have Russell's, I forget where he first, I think it's in his introduction to mathematical philosophy that he wrote in prison, by the way. He millionaire, but has an infinite number of pairs of shoes, an infinite number of pairs of socks. And he calls this Valadin one day, he's an eccentric, of course, and said, would you please select one shoe from each of my pair of shoes? The valet says, oh, well, how shall I do that, sir? The millionaire says, oh, we'll just take the left shoe from each pair. Right? Make a big pile of them. And then the next day, his fit of eccentricity, hasn't died down, and he has his valet come in and says to him, well, I'd like you to select a sock from each of the pairs of socks that I have. Could you do that, please? And then, of course, the valet asks the same question. Well, how shall I do that, sir? And of course, the millionaire can't think of how to do it. He can't say take the left-hand sock. There is no intrinsic way of distinguishing the socks, right? On the other hand, right, that shows the difference between the idea of making the selection, where you would have to give a definition of it, which would be, right, it's rather clear the constructive element in that. But how do I do it? That's to say, well, it's possible in principle, but there is the result of however you got it, whether you made the selections or not. It would just be a pile of things of socks, and there'd be exactly one sock in it from each of the original pairs. Those two ideas were sort of identified, and that was a mistake. Because the Zermelo later tried to clarify all this in a second paper in 1908. Of course, he had a reason, because he was trying to prove that every set could be well ordered, which is an essential part of Cantor's theory of cardinal numbers. But anyway, it got confused at the and so it was called non-constructive because it is quite true that that form of the axiom of choice, as in the case of applied, let's say in the case of the socks, saying that there's one sock you can get from each pair, is non-constructive. Doesn't tell you how to do it. Now, the interesting thing is that the term non-constructive, and that's how I learned the term non-constructive. Well, I thought it meant, right? An argument in set theory using the axiom of choice was non-constructive for that reason. The axiom of choice doesn't tell you how to make the selections, but on the other hand, it doesn't have to. It merely asserts. See, the thing is, arguments in classical mathematics don't have constructive built into them, but mathematicians were well aware, even before that, the notion of constructive arguments and so forth had been fully worked out. They knew the difference between actually producing something or telling you how to do it and simply asserting its existence. Of course, mathematics was never entirely Platonistic, if you like, in that way. What was involved? It isn't as if classical mathematicians abandoned the idea of evidence or didn't have the idea of evidence altogether. But the requirement became much stricter with constructive mathematics. Now, what happened? So that's why the source of the term non-constructive in in, uh, in classical set theory with the axiom of choice. Now, one of the things that, again, tiny bit of historical detail. I only really got interested in topos theory and also in construct, not in intuitionistic mathematics, when I came across the proof when it was shown that the axiom of choice implies the law of excluding middle. If you take the axiom of choice, take set theory, your usual axiomatic set theory, and just use intuitionistic logic instead of classical logic. You've got to make slight modifications to some of there, but basically that's called intuitionistic set theory. In 1975, Radu Diaconescu proved that the axiom of choice, stated in the usual form, and any of them, really of the usual forms, in intuitionistic set theory, implies the law of excluded middle. Amazing. I mean, what an extraordinary thing. It's actually a very simple proof. He used to do it as a Apollo trick, the students. It's very nice. Anyway, and the original source of this actually isn't the argument isn't from logic at all. It's work in category theory. It was thought that if you interpret this in category theoretic terms, then the axiom of choice, which is there are many forms of the axiom of choice. There are hundreds of them. One is that's particularly the ones the category theoretic use, that every onto map, every surjection has a section that you can invert it, so to speak. That's the form that's used in category theory. Okay. Now, anyway, that's neither here nor there really. But the point was that this showed in some way that the axiom of choice is deeply connected with constructive, right? Is non-constructive in that sense, in the sense that if you have it, then you can derive classical logic from it within set theory. Every set theory without not an intuitionistic set theory. I thought that's an extraordinary result. And I got that 40, 50 years ago now, but I mean, it just blew me away. And I got into stuff that converted me to an interest in constructive. An odd way of getting at it, I guess. It was really through category theory. But anyway, now, I'll tell you another thing. I remember one of my friends, we were students together, Dan Isaacson, who was a philosopher of mathematics, retired. When I told him this result, he said, "Oh, well, but how can that be? Why? Because he was acquainted, which I wasn't, with the interpretation of the axiom of choice in type theories that have been merged with, where the axiom of choice is provable in intuitionistic type theory." Why is this? How can that make sense? How can the axiom of choice both imply the law of excluded middle and yet be compatible with systems where the principle of excluded middle is incorrect? That's really subtle. It turned out that's a very subtle issue. I mean, I'll tell you what it was, why this comes about. Because there's another form of the axiom of choice, which is conversion of a universal existential statement. So if you say, for every x, right, there is a y, such that Rx1, x and y are in this relation. Then a form of the axiom of choice asserts that then there's a function, right, on these objects, which are x and y are variables ranging over f, such that for every x, right, r fx is related to x. In other words, you've selected such a y. It becomes a function of x. Yes, but that the meaning of the quantifiers in constructive type theory is just that. You can't assert for all x there is a y. It's without actually having such a function. Again, it's the same constructive idea. That when you say that there is an x, you see what I mean? When you say there is an x such that has a certain property constructively, you have to give a procedure for producing that x. When you have a doubly quantified statement, an alternating quantifier statement like for every x there is a y such that rxy, you have to supply a method. It's implicit that you supplied a method, it's a recipe that when given an x, it produces a y such that that y is related to x, and that's the function. Yes, but that's built into the meaning, right, of the quantifiers in constructive type or constructive reasoning. Hence, the axiom of choice is true. The axiom of choice is implicit in the meaning of for every x there is a y. Now, of course, we got a while to understand how that comes about. That's why another reason why the axiom of choice is interesting. It's both constructively correct. It's both constructive and non-constructive, depending, right, on the background, the background framework in which it's interpreted. In the truly constructive framework, the axiom of choice is correct. In these hybrid frameworks that like taking classical set theory and getting rid of the law of excluded middle, the axiom of choice implies it's very strong. It actually then implies the law of excluded middle. Whereas in a fully constructive context, it doesn't. Well, that's as you can see why, and it's all. So there were several issues. One, does the axiom of choice, does it really require choices? Well, yes, it does in some formulations. Russell called it the multiplicative axiom in Principia Mathematica. You know, Russell Whitehead, famous work what he reads. There's only about 3 people who actually read it, apart from the authors. Gödel was one of them, apparently. Amazing. That there they interpret, and it was pointed out, well, implicitly in that system, they are talking about functions and objects which are in some way definable. And that was a source of but it doesn't even matter whether they're definable in these specify the law of excluded middle. Just the form, any form of it, will actually imply it if you just take ordinary set theory and use and base it on intuitionistic logic. But if you take these ideas seriously of the meaning of quantifiers, then the axiom of choice is actually correct. And there's a type theory. This was first observed by who? Martin Löf, possibly. He's the old man. He one who really developed the idea of constructive type theory in the 1970s. Anyway, axiom of choice has a very tangled history, and not only that, it turns out you can show that but the fact that you have this that it's true constructively has been a source of genuine confusion. But then it started in controversy, and yet the axiom of choice is obviously correct for the notion of just of a simple undifferentiated collections where you don't care how you get, just look at them with grab bags. You don't have to tell them. You don't actually have to tell how to produce these objects. But in the constructive case, fully constructive, you don't have a version. Well, there are versions of where you try to mimic to say, what does the classical case mean constructively? Right? You have this idea that the constructive reasoning, that implicitly statements are understood as having implicitly there's some kind of way of producing evidence for asserting it. And then you try to find formulations, other principles that actually enable you to get classical reasoning out of this? And there are several. I mean, one of them, as I said, is the axiom of choice in the set theoretic system. Others, there are things like function extensionality. It turns out the whole issue is very subtle, and it's interesting that the classical mathematicians who really weren't interested much in the some were, of course, but in the interested in proving theorems about classical mathematical objects and concepts. Yes, the axiom of choice did give them pause, because it did seem it was subjected to initially, in the early days, by what they call the semi-intuition, semi-constructive. Like there were French mathematicians, for example, Borel and others, who rejected to the use of the axiom of choice precisely because how do you produce an object that does this select? And I'll tell you one finally there. The idea was the reason it was used, it was to prove that the real numbers could be well ordered. That was the main theorem as a mental. Cantor had thought, because you need this in order to be able to on arithmetic, of course, in Cantorian set theory. Well, Cantor never was able to prove it. He just assumed it. He thought, well, it's sort of, he gave some quasi-philosophical argument that you can always take any set, in principle, you can put it in a well order, with the first element, the second element, and so on. And then that could be then extended into the transfinite. Well, he didn't prove it. He just took it. Well, that's a kind of principle. So Mano isolated it and then proved it using the axiom of choice, right, as he formulated. But then the way that was objected to, because in that case you should, if you use the axiom of choice to get a well ordering of the real numbers, how do you get it? And where does it come from? It's just to come out of the air. Nobody could visualize a well ordering of the real numbers. What does it look like? How do you get it? Well, then it was actually shown later. I think it was Levy, 1960s, actually showed that in classical set theory, never mind the constructive interpretation, that in classical set theory, it's consistent to assume that you have a well ordering, right, of the real numbers, which you might have gotten by the axiom of choice, but you don't have a definable one. That's a beautiful thing. In other words, all of this whole issue, right, didn't come clear until the sort of 1970s. And even then, even now, of course, there's stuff going on about versions of the axiom of choice in constructive type theory. And this new area, this homotopy type theory, which is a big deal these days. Vojevodsky's ideas. And but anyway, you can see it's a rather tangled tale. And yet, it's quite true that the only axiom of set theory that is known to most mainstream mathematicians is the axiom of choice. They don't know any of those. Then they don't have to. It's not necessary. Whereas the people working in constructive mathematics understand this axiom of choice very well, because essentially what's happened is in the way that the classical, algebra and category theory think of the classical view is it's the axiom of choice, and yet the axiom of choice is also constructively true. You've got to be very careful about the meaning. The two things can have the same form. Of course, we know that in mathematics, but what did Poincaré say? Mathematics is the art of calling different things by the same name. It's Poincaré's famous statement. And that's true. But then if you do that and you're not careful, right, you don't realize that you're actually talking about different things and you're giving them the same name, as in the case of the axiom of choice. The one, if it's constructed, is about meaning of the quantifier. In the classical case, it's got nothing to do with that. It's just a sort of combinatorial statement, taking things out of bags, if you like. Anyway, so the axiom of choice. Why were people wondering about the axiom of choice? Well, it wasn't that was That was a question, but they weren't claiming that it was producing crazy concepts. Later, of course, it did stress it, like the Banach-Tarski paradox. Well, you know that you can split a sphere into two, two small spheres of the same size and so on. Yes, but again, that turned out to be the case because you take continuous things like spaces and you split them up into points and make them sets. Yeah, sure. Once you do that, they can be rearranged in all kinds of crazy ways. Why? Because you don't have continuity anymore. Not everything. The Banach-Tarski paradox is, of course, it implies, of course, that you have discontinuous functions. I mean, in a rather elaborate way. But if you're working in a completely smooth world, or a world where you, which is consistent actually with, with intuitionistic logic, then you don't get situations like. But the axiom of choice, that's why when Gödel proved the consistency, the relative consistency of the axiom of choice, whatever it was in 1938, it was an important result. Although the continuum hypothesis was the main thing he was looking for. But in other words, you weren't going to get any contradictions from the axiom. And nobody really thought, it's very interesting. The axiom of choice is a completely intuitive thing, for ordinary undifferentiated sets. Yet it had what we call paradoxical consequences. But that really wasn't the fault of the axiom of choice. It was because you're thinking of continuous things like spaces as represented discretely by collection sets of points. It's not the axiom of choice. The axiom of choice is correct, right, for the collections of points. It's not correct, on the other hand, if you think of it in terms of continua. And that's the source of these. There's been a lot of, I tried to explain all that. Well, of course, it's not only me, but I wrote this book on the axiom of choice about 12 years ago. I tried to get that into all that stuff at the end. And it's quite difficult to sort out. I mean, it's all pretty well understood now, but it was they said Frankel was, I think it was Frankel, absolutely right. I mean, after the parallel postulate, Euclid's fifth postulate, the axiom of choice is the most interesting and the most discussed. Anyway.
Okay.
So,
John, I would like to ask you regarding the continuum concept, whether you can describe what is the true nature of the continuum, whether it is a purely mathematical abstraction, or does it have an intrinsic connection and meaning to the physical world and to the nature of reality?
yeah. Well, first of all, yes, of course, the continuum is one of the primary concepts. The continuous is what Brentano called a unitary intuition. It was an intuition built into intuitive thinking, into intuitions of the world for how long? I mean, time immemorial. It was the ancient Greek philosophers who talked about continuous and discrete. Okay, so top of the continuum, but continuum is the objectification of the idea of continuity, or one of them. A continuum is a that doesn't have gaps in it. The mathematical continuum is a straight line. The simplest example, of course, is the usual geometric straight line. It was taken for granted that's continuous. The person who gave the definition of continuous and discrete is Aristotle in his physics. And Aristotle has amazing arguments. I mean, you realize just, he was the first to undertake systematic analysis of the idea of the continuous. And he, as I said, he actually produces a distinction between these. It's in the categories, continuous and discrete. Anyway, yes, the continuum is a primitive notion, as is the discrete. Well, which is actually given first, continuity or discreteness? It's an interesting question. You have continuum, and it all got so to try to answer your question, to stay on the track, in other words, yes, the notion of continuous was simply taken for granted for a long time because the world is given continuously. It's not an abstraction directly. It's a unitary intuition. Well, of course, then it became important. It wasn't important in arithmetic because arithmetic is concerned with discreteness. And then they had problems about, in the case of arithmetic, they had the problem about what is a unit. The Greeks called a number, it's a collection of units. That was their definition. And we still use that. But the continuous, on the other hand, really meant connected, like the term continental. Yes, and so in a way, it's interesting. Probably the notion of discreteness is some philosophers thought they took the idea of continuity more or less for granted, and 9 out of 10 philosophers over. I wrote another book on that one from the ancient, well, even from the ancient Greeks on, simply took the idea of the world being continuous, space, time, and even matter, right, as continuous. Discreteness was the odd notion. That was the abstraction, you know, and you still have the idea, philosophers saying, well, discreteness comes from the world really is a continuous flux, okay? And so when you select something from that flux, remove it from its natural continuous flow, that's where you get discrete things. Or the idea of change, the philosopher expressed that in a succinct way, was Heraclitus. You can't step into the same river twice and all that. So all I'm saying is that the notion of the continuous is probably it seems to have been something that's simply initially given to us. Now, of course, then the question is that wasn't precise enough for mathematicians. Not at all. It was true. In a way, you could give a precise definition, mathematical definition of continuity wasn't given until the 19th century. I think it was Cauchy, probably early 19th century. What does a continuous function mean? Right? And but yes, the idea, the issue, and now I think is it's kind of objective question as to whether the physical world or the material world, the world given to us by physics, is it continuous or discrete? See, the quantum theorists haven't decided that one. There's still no proper theory of reducing, because the program of physics, program of mathematics too, was the reduction of the continuous to the discrete. That's what set theory did. That's what they were trying to do in the 19th century. Oceana, the virus struck, trying to make the idea to introduce precise definitions of continuity in terms of discreteness, because it's the discrete where you can make a precise definition. In case of numbers, they hardly had to bother with it in the case of numbers. It didn't really matter in a way whether arithmetic wouldn't have changed however you defined a number. A number is a collection of units. Well, that sounds almost circular, but actually that is the definition in Euclid. Then, as I say, Frege came along and gave a very remarkable analysis. He said a unit was a concept, But yes, the notion of the continuum was given, the notion of discreteness, and they'd been a classical pair of oppositions, right? From time immemorial. They were in ancient Greece, the one and the many, the continuous and discrete, you can sort of see it as these dialectical opposites. But the fact is that there is even in contemporary physics, the question about what continuity means. It's true that quantum theory has put a whole monkey wrench into this whole question about whether the universe is actually continuous. It was taken for granted it was, probably until Planck, right? And then Einstein, introduced everything, of course, early quantum theory. But even now, the mathematics that's used in quantum theory is continuous. There isn't a discrete version of it. Hilbert spaces are continuous.
It looks like, though, that the quantum theory sets sort of a lower bound on distances to which, after which it makes sense, smaller than
Yeah,
which it makes no sense to talk about, where our predictability and the law of causality kind of stops making
I
sense.
knew we were going to get to this. We couldn't avoid it, could we? Because I don't know. But yes, that's true. But the reason that was very interesting, because it did turn out that at some experiential level, some empirical level, the world, there is an element of discreteness introduced. You can't explain things like the photoelectric effect or the black body radiation without quantum, without wave packets in any way. introducing discreteness. But the mathematics that handles that still continuous. Oh, I don't mean computers making computations. The actual theory. Classical, even quantum electrodynamics is ultimately based on Hilbert space. So these are continuous objects. But that's the thing. When you try to, there still is no real proper discrete geometry. Geometry reduced to discreteness that explains, let's say, something like, well, that's the holy grail, isn't it? Trying to reduce to quantized gravitation. I mean, the Riemannian manifolds that you use to describe general relativity seem to be irreducibly continuous. Mathematics is well understood, even though it's quite true at the set theoretical level, it all gets reduced to discreteness. You say, well, actually, we don't really, because you don't need the notion of continuity, a primitive notion of continuity in set theory. It's an axiomatic theory that is based on essentially discrete notions. And it represents continuity. But of course, the argument is does it really represent the notion of continuous faithfully? Well, there are plenty of considerable number of mathematicians and philosophers who said no. It works, but it produces for example, Cantor-Dedekind definition of the continuum. It's brilliant. For using Cauchy sequences or Dedekind cuts, brilliant. But there were a number. Bertrand Russell was a great champion, of course, of that idea, and he like Cantor did become to think that continuity, the idea was a kind of another dogma, what did Cantor call the kind of dogmatic a notion, a mysterium he called it, and it's true, it was vague, and yet the notion of something continuous is not vague. It's obvious perceptually. It's a primitive intuition, but of course it's true that when you try to analyze it, the tools of analysis weren't more continuous things, they were discrete things. And that's a good old philosophical question. I mean, it still is. But in the physical case, it does seem that the quantum theory is a rather unholy mix of discreteness and continuity. And it's still not been shown enough, as we know. But yes, there is a fundamental level at which discreteness is asserted in quantum, but not maybe, there was the idea that, well, somehow, yes, it's true, there are things like Planck length, right? But isn't that just empirical? In principle, it may be that you can't actually get down to the real continuum, because it can't be done simply on empirical grounds. And yet the world could still be continuous, you see. We're never going to get to it at that level, at that discrete level of discrete analysis. And that may be the view. Physicists themselves do vary quite a lot. And for example, David Bohm, for example, died. He thought that basically the world's continuous, and there are various forms. Of course, he wanted a way of reintroducing causality, or not causality exactly, but realizing the idea that some sort of determinism into quantum, and the idea that at some level the world is continuing. I think the real issue that come up now is not the question of continuity and discreteness. That's the thing that actually drove quantum theory. That's what it's called, quantum theory. That wasn't the original meaning of the term quantum, as Hegel used it. But the idea that things come in it's basically atomism. And atomism was interesting. Atomism was not the common view of philosophers. It was regarded as, Epicurus, and then from Democritus. But now I think the issue is in physics. Again, I'll just say one thing on that. It seems it's not that so much that it's there because of the problem of quantizing gravitation, but no, it's a question of locality. Bell's theorem. Bell's theorem, because I had letters once my name is very close to his. John Stuart Bell and John Lane Bell. We never met. I was unfortunately I never did get to meet him. He died quite young. Well, he was in his 50s. Anyway, but the thing was that it's interesting there that the locality thing, which is now the main issue, I think, the thing really driving it. the fact that Einstein was wrong on that. But non-locality is perfectly consistent with continuity. Of course, it's easy. You can produce topological models of these sorts of continuous spaces and have that sort of problem. Non-locality, but it's true. Locality, actually, non-locality is much more connected with discreteness. If you have a continuum, you can imagine all the parts being connected. That was the view, for example, of the Stoics and the Greeks. Actually, substances are continuous, and each one, when you have a vibration in one part of it, it vibrates. That's non-locality. Non-locality is very difficult to understand if you have discreteness. It's relatively easy to understand if you have continuity. You look at waves, wave motion itself is non-local. No. Sorry, I wasn't going to get on to that. It's half your fault.
John,
Always
what do you believe?
you.
John, what do you believe the relationship between mathematics, physics, and philosophy to be? Because as we have been speaking, well, we
Huge
have seen that
question.
we have been speaking about mathematics and then physics, and then on some, let's say, in some times, we have been sort of diverging into more philosophical sides of mathematical inquiries. So, what is the relationship between these three areas?
Well, if I give you, they wouldn't have retired me if I had the answer to that question. No, I was, no, I retired myself. That's not fair. But well, first of all, again, I suppose it's helpful to take some kind of historical view on it. I mean, philosophy, mathematics of the is in its specific sense is probably the oldest, which had a definition. It's Pythagorean. I mean, mathematical practice, of course, had been there before. I've been in Egypt, but it was mainly a practical. So I tried to explain, my little prologue. Okay, it was the Pythagoreans really who were the first genuine mathematical philosophers, and they thought the world was something like arrangements of numbers or objects which could be expressed in terms of numbers. Okay, philosophy meant and mathematics meant knowledge. I'm not a Greek scholar, it means, but that's what it meant. Philosophy meant lover of wisdom, yes, but that's much vaguer. You can be wise without really knowing very much. You know. Physics, yes, but that did mean essentially the world of these things that can be seen to the senses. I mean, the nature of the outer world. Now, of course, the atomists thought apparently the inner world could be explained in terms of the outer world through atoms. I mean, it seems to be what Democritus thought. It's certainly what Epicurus thought. And Epicurus, of course, was condemned not for that, but of course for his views on pleasure and so forth. But at any rate, all three of them, right? And if you look at a good, useful way of looking at it is there's no. It's interesting that in Aristotle, who was a great classifier, and categorizer, there's no work. There's no the word philosophy doesn't occur, as far as I know, in any of his titles. Ethics does, the Nicomachean Ethics. Metaphysics, yes. Philosophy really got identified, at least the main part of it, with metaphysics. Ethics didn't have much to do with physics. Metaphysics, metaphysics, beyond the actual physical world. And even now, it's true that there is a kind of a sort of trinity there, which is interesting because it's a part of physics, mathematics, and philosophy. They do sort of hang together. I mean, although if you examine the reasons that they hang together, it's a sort of quite a complex historical matter. In the case of philosophy, is turned into through metaphysics, which metaphysics really is about ontology. What is there? And of course, you could say that's very general. So that would include physics. Now, would it include mathematics? That's interesting because mathematics doesn't talk directly about objects. You have to do something to make it, to objectify it. Otherwise, It's not talking about, let's say, what is there, maybe practices, you could say, in mathematics. It's true, there are parts of math where you could say it is just about numbers or geometric objects or whatever. That's why algebra was a sort of turning point, really, because what's it about? Well, we don't know. X, Y, and Z, or X, Y, and Z. But yes, the three still, but it's interesting how in the case, the physicists, like Hawking, didn't have any time for philosophy. But then these guys, and Richard Feynman, he was great in many ways, but really he was a bit of a Philistine philosophically. Some of them are. Oh yeah, brilliant man. Why? Because philosophy then became concerned with things that don't actually, metaphysics properly isn't even regarded by many philosophers anymore as a genuine part of philosophy. I mean, they made that effort in Oxford, in the middle of the century, the linguistic philosophy, just analyzing words. And metaphysics is nonsense. And the positivists had that view too. But it's interesting that the positivists were very strongly influenced by physics. In other words, not by physics, theoretical physics directly, perhaps, although that did play a role. Some of the people were very close to the theoretical physicists. No, but in terms of what could actually be measured or some empirical, but it's a form of really of empiricism. But the point is that all the mathematicians on the whole have had the that I think they were probably more philosophically inclined than physicists, but then mathematics and physics were hardly distinguished, 300 years ago. Physics was natural philosophy. You weren't called it, even now, Cambridge, the professors of natural philosophy, not physics. And what was meant was, of course, I mean, it hinged on a word, but it does show the connection between philosophy and physics. Natural philosophy meant philosophy of nature, which naturally exists in the outer world, and we perceive it. So yes, there are big connections, and there's been this toing and froing, from one to the other, and rejection of Hawking, for example, would reject philosophy because he didn't like metaphysics. But then there were plenty of philosophers who didn't like metaphysics either. So yes, but it's true that those three areas have been very important. I mean, I think in probably most sort of developed cultures have different views about it, but about the nature of each one. And of course, in the case of physics and mathematics, Galileo said, nature is written, and the book of nature is written in the language, which brings in another point, right? And that, of course, introduces problems because you don't. How does nature know? Well, to be mathematical. Well, the simple answer: if you're religious, God did it. Simplest answer. It's not acceptable to me, but it's a very simple answer. Anyway, so I think no, and what's again another point in that connection. It was thought mathematics was still undergoing problems in the 19th century before before quantum theory. There were some sort of problems with it, but basically by the 1880s, it was still physics was sort of completed. All cut and dried, all sort of known. Atomic theory had worked very well in chemistry, and which is true. And essentially, some kind of atomism was supposed to prevail, and it's still there to some extent. And then there was this revolution, right? And indeed, the question of philosophy and physics was not very interesting anymore. We know what the world's like. And it's true. There were fields. It was Maxwell's, stuff coming from electromagnetic theory plus atoms equals completeness of physics. Yeah, okay. Well, then the photoelectric effect, black body radiation, and then the quantum revolution. Now, the effect of that was to reintroduce philosophy into physics. I mean, the most interesting philosophical debates that you can read are those between Einstein and Bohr. These are two physicists. 19th century wasn't as interesting at all. It was all pretty cut and dried. I mean, there were philosophers of science. I mean, what they were really describing, they weren't describing revolution. I mean, where the fundamental nature of what's being discussed was in question. So you got these. Who am I trying to think of now? The French positivists in the 19th century. Well, of course, then you talk about scientific method. Poincaré was very interesting on that. But again, there's a guy who combined all three: physics, philosophy, and mathematics. Lots of great universals. So I think the effect of quantum theory and these has been to re-inject philosophy, or philosophical questions at any rate, problems into physics, and they still go on today. And particularly now with cosmology, well, cosmology, I think cosmologists should be writing science fiction. I think they are actually. But I'm particularly interested in this because I want to be a cosmologist. I studied with studied. I went to like Fred Hoyle's lectures over many years ago, and but again, because the speculations about physics, about philosophy, and cosmology go on again now because Big Bang. I mean, that's well, and also theology, because it's a re-injected theology into all this. I didn't talk about theology, but theology ought to be in there because theology used to be part of philosophy, or an element in it, of course, uh, and in physics, the natural world. It's in mathematics, maybe not so much, but so yes, I think that there's the development of all of these fields, particularly I think recently in physics, has reintroduced philosophy into arguments about. And yet, of course, physicists like John Stuart Bell, not very brilliant and very sort of down to earth analysis of what's going on. But the fact is that the questions that are arising there are actually philosophical questions, whether the whole business of Schrodinger's cat and so on. It's still there. It's just physicists, they're so used to it. Now they regard it as an old hat, but not by everyone, by any means. And as I say, it's not it's non-locality that's the current problem. So philosophy hasn't disappeared, and it was thought you didn't need philosophy or any kind of metaphysical up until quantum in the 19th century, and everything looked cut and dried in physics. Not so in mathematics. There were still arguments going on about the nature of the continuum there. And it's true that set theory was supposed to solve all those problems, but it didn't. But nevertheless, it was a way of talking about mathematics as if it was just reducible to set theory. And set theory has been very successful at reducing everything, mathematical notions, whether they, in particular, notions which seem to depend on this, some kind of intrinsic or irreducible continuity to discreteness, just like trying to explain mathematics in terms of numbers. It's Neo-Pythagoreanism, really. Anyway, so yes, there's still this interplay, I think, between them.
Okay.
And yeah.
At the intersection of these three areas, mathematics, physics, and philosophy, there probably lies one of the most, at least I hope, one of the greatest concern of the 21st century, which is the problem of consciousness. And I would like to ask you, I would like to ask you
I've
if you
thought a
had
lot
to.
about that. I've written, I don't know if you've seen it, there's a lot of occasional writings on this topic that I've thought about for a long time. It's very difficult to make any progress because there are so many parts. I think the real difficulty there is the fact, well, it does seem to be a fact. If somebody could show you could have disembodied consciousness, it's not inconsistent. I don't believe it. I don't think it's logical. Husserl, Husserl was he's being taken more seriously again, I think, in phenomenology. He part of he did question consciousness was his primary area of study, and he did this thing about isolating. He was a mathematician again, as you know, interesting. He then And in phenomenology, you take consciousness as as a given. It isn't it really. It's something that is there, and just don't question it. If you does a thing called bracketing and epoche, you you just treat it as it's actually given to what, but given to whom? Well, that's the other problem about subjectivity. Consciousness isn't, well, of course, there are theories that the Vedantism and so on, which I'm quite attracted to. I don't really believe it exactly, but the idea there's a universal consciousness. See that the thing is the difficulty I think with conscious, at least in practice, is that it does seem to be connected in the subject, right, to the actual functioning of a brain. I guess. I mean, it's manifested. I there are people who think the consciousness is just quite independent, like space and time. Why not? I mean, Weil wrote a book called Space Time Matter. Wild like materia in 1919. At the same time, amazing. It was published in 1918. At the same time, he published this book on the continuum. Anyway, he should have put consciousness in there because he was a phenomenologist at the time he wrote this. So the title of the book should have been Zeit Materia Phenomenology, Consciousness, Bewusstsein, whatever it is. Uh, and I think that's the context is that the argument is going on that it's very difficult to see how it is that if consciousness has to be localized in the sense, well, you could say localized, but that still doesn't explain the phenomenon. That it's a necessary, could you say, a necessary condition for subjectivity, if you like, or consciousness, is some material process that's going on. All right. Well, I have to say that I'm enough of a materialist at that level to accept it. Yeah, but that doesn't explain consciousness at all. Because it was the same argument they're having about qualia, and then the idea that even if you knew all this, I mean, even if the universe were, or if they were robots, it doesn't make any difference. You're not going to find the source of consciousness, I don't think, or subjectivity in the substrate that actually manifests. I don't believe. What would it look like? What would the Husserl didn't make that question. That's a separate question. The mistake exactly is to say, well, we're going to find. Oh, now I know what it's like. Now I know what it's like to be a bat. I I do like that. What's his name? Name escapes me now, but I have to remember what is it. The idea that there seems to be a connection between just, well, okay, do you have to? It's a similar question in a way to the old question about whether you can have time without matter, whether you can have time without change. Well, Newton seems to have thought that, and so did his teacher Barrow, who famously said, whether things are moving or still, whether I'm asleep or awake, time pursues the even tenor of its way. Nothing to do with the. In other words, it doesn't need a subject; it's just there. Now, of course, we can't say the same with consciousness. Is deeply connected with time, because I mean, it's pretty obvious. It's subjective time, and then we make a distinction between the two. That's why Einstein was not very well understood by, again, his philosopher's name is escaping me. But they had these famous debates about the nature of
Niels
time.
Bohr.
Sorry?
Niels Bohr.
No. That's the physicist. This was the philosopher
Ernst
who
Mach.
wrote Matter and Memory. He won the Nobel Prize. There were only two philosophers. He and Bertrand Russell, I think, his name now. But anyway, that the idea that there may be no subjective time, but like the idea of the present. I like the phrase, because it's a wonderful thing. No time like the present. Well, that's the only real time for consciousness. The present. As Aristotle pointed out long ago, he didn't connect it with consciousness. It's interesting that none of the ancient Greek philosophers isolate the idea of consciousness in their philosophy. I mean, it's there implicitly, but Aristotle more or less takes it for granted. Anyway, uh, you could have the idea of time without anything else. You probably could have a timeless space too. Well, Einstein had to consider that all those ideas when he produced his models for cosmological models. When he not long after he developed general relativity, and but the notion that you could have consciousness without a substrate. Well, of course, that is the view, or an idealist that's all there is. It wasn't really all this the things that we see in the outer world are all them illusions, but they're only illusions in the sense that you're mistaking their actual identity, not that you're not actually having some experience. So the contra really is when you read these works, the result could probably have a complete description of the brain. It's hard to doubt. Given what's been done and understanding the actual connections between, well, it's true, outer measurements and impressions. When they do these things by inserting various probes into the brain and so on. Yet none of the experimenters have the same subjectivity. Where's the subjectivity? It's generated in some way, by the way, presumably. And I think that is a fundamental problem because it may be that the world is sort of given, and it's also tried to say, well, there's only really one substance called neutral monism. There's only one substance, really, and it depends on the way the perspective is taken on it, whether it's mind or matter. Well, that view is still around because it's still very difficult, unless you're dog to say it's all just a complete not delusion. Like Dennett, Daniel Dennett, a philosopher I don't like much, but he's very clever. He died recently, by the way. Maybe that somehow really it's all the subject is it's all just superstition. I don't believe it. But the thing is, if you could build a machine, presumably. Well, of course, which have consciousness in some way, but since I can't identify your consciousness directly, see, that's another puzzle. The idea of being universal. We're not all immersed. We're not, unless you have the idea of universal consciousness. Not absurd. We're not all immersed in the same world. There is a thing called there is individual subjectivity. At least I have no experience apart from individual subjectivity directly. Now, is that connected with the brain? Well, presumably in some way. But the fact is, you could have a mechanism that was like the brain, would look exactly the same physically, and it would be so. There's no examining it and saying, oh, well, now I understand what it means. Right? Now I have the experience of your subjectivity. There seems to be a real problem with that. And yet, it's definitely, consciousness is definitely connected with that, I think. I mean, who knows? Maybe when the brain ceases, it dies off. Maybe, consciousness is a subject. I don't think it could be the same subject exactly, but that somehow there's some kind of, a lot of people believe that. Good reason. It's rather consoling. The idea of permanent cessation of consciousness is, you envy the animals and that, but presumably they're not equipped with that. We don't know. But really, the issue is, first of all, can consciousness exist? Consciousness does exist. Two ways. Can it exist without a physical is it necessarily connected with the brain? Well, Ursula mentions that question here and there. He's not concerned with it directly. Of course, for his purpose, it doesn't really matter because you're talking about pure subjectivity. Is it pure subjectivity and abstraction? Yes, it is for physics. But it's not pure subjectivity isn't an abstraction for the individual subject. Then it would say, well, actually, this is Gilbert Ryle. These people really didn't like he called it the ghost in the machine, Didn't think that there was even subjectivity in that sense. That was also a kind of, I don't believe that. I think the simplest answer, which of course that doesn't really work, is Cartesian dualism. Cogito ergo sum and all that. But then you have this problem about, Leibniz had the problem. He had to produce this crazy idea that they're all wound up, right? So it's running at the same rate. It's a problem, right? But the idea you're going to get rid of philosophy altogether and reduce it, the idea of consciousness and so on to the brain, I think it's a non-starter. And yet there will be and that's called these days. I don't like the term, but there's this fellow. I'll probably get older names. The idea that we just don't have the mentality to solve what's called the hard problem of consciousness. I don't think that's the issue either. Although it's true, if you start to think about it, you think, well, where is the subjectivity? See, you really want to, then you have to take some kind of view that these things report that you are not going to find the answer to subjectivity simply in brain chemistry. And yet, if you didn't have brain chemistry, brains, you might not have subjectivity at all. Maybe, but that's where it differs from time. I think time continues to exist, whether in consciousness or not. I think what consciousness does, not subjectivity necessarily, but consciousness, it actually produces the idea of the present. And what does it mean to have the present? Of course, it's a mathematical abstraction to say that there's a present, there's a point. But what consciousness seems to do is it embroiders, or at least it pinpoints notions of the present. Because why? Because subjectivity doesn't exist. Aristotle pointed out subjective time past no longer exists for the subject. The future doesn't yet exist, and the only thing is the present. And he thought it was just a boundary. He says so. So I do think consciousness is connected with all of this, but I think the argument is how. Never mind why. That's a theological. Okay.
Definitely. John, do you believe that during the 21st century will humanity see a Nobel Prize achieved for understanding, unlocking the nature of consciousness?
I don't know, but in physics, I don't think so. If it's in physics, if it's in philosophy, well, that's different. Right? There have been Nobel. Well, what about? Okay, there is no Nobel Prize in philosophy, but there have been 2 Nobel Prize winners who were philosophers, literature. Russell and damn it, remember they come. Suddenly pop out 3 a.m. Yeah, no, I don't think so. I don't think consciousness really is that. It's no, because it really is trying to eliminate consciousness. See, that's another thing. Some of the really bold, they're trying to eliminate space-time. You read these physicists, they say really that the fundamental level isn't space-time at all. What is it? Some kind of discrete lattice. But of what? You see, that's also a lot of these programs are, and of course they produce remarkable results, are really eliminative. For example, getting rid of continuity and replacing it by discreteness, right? Getting rid of, I don't know, the theologian will say getting rid of God, and having mechanisms, that sort of thing. But in the case of and these eliminative programs have worked extremely well. That's what behind the whole lot. Some are rather dogmatic, getting rid of religious notions. Like I don't like personally Dawkins, really no Easter. And then the idea that everything can be explained by evolution. Well, of course it can't, but evolution again probably is necessary, right, for these structures to emerge. It doesn't explain the detail, but why should it? Anyway, but the other so. If you got a Nobel Prize in physics, that would just be eliminating consciousness. See, elimination it is part of explanation. That's quite true. I mean, certainly in physics, they got rid of Well, although this teleological thing still comes up, but not directly in physics. Well, how do these electrons see? The great, wonderful thing is they've been in the case of quantum theory, for example. With the two-slit experiment, say, any of these classes. How does an individual photon know which slit it's going to go through? You put it doesn't. It's completely random. Well, it's statistical. That's completely random because there's statistical. So you just eliminate the question of which one. It's eliminative. And that's interesting because it may well be the case that you can genuinely get rid, right, of certain notions that that were thought to be there objectively. For example, well, determinism, but then determinism has been questioned for a long time. I mean, I suppose, most penetratingly initially by David Hume, right? I mean, Humean empiricism, and well, we don't know. We have no direct evidence, and we never will. The sun is always going to rise. It's just a sort of inductive generalization that we make. Now, does it have anything to do with the actual? Yes, but we don't know that. Laplace would say, yes, of course. I don't need God to explain how it is that the world, it just set into motion and goes like a clock. You don't need anybody to watch it. But in the case of something like consciousness, it's much more slippery because it involves sort of notions of identity. It involves all kinds of areas, epistemology, temporal awareness, and whether it's really illimitable, that you will know more. What will you know more about? Your own consciousness or somebody else's notion of green? Yet you'll be convinced that somebody would have to be convincing, saying, well, actually, consciousness would be part that would see there would be a more plausible mechanism for how a subjectivity is generated, but it wouldn't tell you that what the conscious experience of subjectivity was like. It doesn't have to. The dogmatic part would be to say that you don't have it; it's an illusion. But, oh, yes, all right. I don't think you take consciousness as a subjective notion, you're going to get a Nobel Prize in physics for trying to find the mechanism. But you might well, particularly in brain chemistry, would make the whole idea that brings the idea of the subject closer to the notion and does seem to explain that it needs to have a physical process undergoing it, but undergirding it, in order for it to exist. Just as you have to have water, but you still have to have the water for the river to flow. I mean, but yeah, I think that, and yet, not one of the I read a fair number of works on this. They never it makes it they're these mathematical. I tried it myself, trying to find a mathematical description of what a subject would be like. Well, I don't know. You do some categorical analysis. Of course, nobody's seriously saying and doing that. Certainly, I wouldn't. But then saying, "Oh, well, I got now some features of subjectivity, mathematical properties of." Yeah, but that's not the actual mathematical description. Mathematics has never really claimed to be well. Pythagoreans thought so, but usually the book of nature is written in the language of mathematics. It isn't mathematics itself. Galileo didn't. No.
John, if you had woken up from a 1,000 years nap and you had to ask only one question, or let's say, what would be the first question that you would be asking to someone living in 1,000 years' time?
Well, the first thing I think would be so astonishing. You probably think that this is an illusion. If I died 1,000 years ago. No, it's a good question. Well, it's a good question you find in science fiction writings. No, it may be. Ask them. It might well be that you're asking some sort of machine. First of all, it could be, and we're not sure now already. Well, first of all, is we haven't. I suppose probably ready to go. We haven't gotten blown up yet. That's another question. But no, the I would be surprised if you ask the question, sort of philosophical question. You say, "Oh well, what do people think about consciousness? What has been in progress?" Well, it might well be that the case, as in this is some science fiction. I mean, there are intelligent machines, and then the issue will be whether they have consciousness. Has it ever been decided whether these machines, actually feel of the same? And then real progress would be, oh, I can't understand the question. What difference would there be between me and my buddy
Definitely, probably would be one of the
Robbie
most
the
interesting
robot
ones.
over here? Yeah, because it isn't clear how. Yeah, and of course, um, the would the question be asked? It's rather when you try to write, what would a middle age, say, century? It's funny because the really interesting thing about a question like that now is that it is thought, assuming we don't blow ourselves up and so on, we have to join Elon Musk on Mars. I wish he'd go to Mars as he's turning into a real nuisance. He's going to get Trump reelected. Anyway, the as to whether there would really be such a radical change, say that by some, it would probably have to be some development in terms of machine intelligence or something like that, where we just change the whole framework with which these questions are on. Because that's not particular. We still read ancient literature. I mean, presumably when you read ancient Greek, yeah, they're asking this similar question. They didn't use machines and so on. But the really is would be the sort of meta question about what kind of question would you have? Maybe the whole framework will have changed so much. But it would be like, would that be evolution? Well, yeah, it was like asking a Neanderthal or a very early hominid, these sort of questions. Presumably, you wouldn't know what you're talking about. I mean, never mind whether because of the language, not just that. It's able to have the same sort of feelings. But it's true, 1,000 years, who knows? I mean, but as I said, the chances are that there will be, since there'd have to be such an exponential, a profound change, because we could still read the literature of 1,000 years ago. Will in 1,000 years, assuming so. The other issue is, did we ever get off the Earth? I mean, see, that doesn't seem very likely unless you set wormholes and so on. Oh, I love the idea of wormholes. I know that we're probably stuck here. Um, but I do think it would be whether there's still going to be some common framework for communication with somebody, let's say, of our time. And in 1,000 years, it isn't clear. Well, they do, by science fiction writers do send people to the far future, and they send them into the past too, and they have to try to figure out. Well, they have to write a saleable novel or short story or whatever, so they have to have some basis for communication. Anyway, so
Okay.
but when did they ever find conscious that old notion? Well, you can read Brave New World. I mean, there were actually did. That's probably a better, I think, more than 1984, which is an amazing novel. That would be depressing, but no, the idea that there would be some sort of like progress or call it progress, change, where well, in the case of Brave New World, it's 626 years. It's Brave New World was written. It's 600 years in the future in Huxley's novel. 19. And of course, he has to maintain a that has asked the same kind of questions. But there's a whole load of other people. The question would be meaningless. So I don't know. Oh, I haven't really have. Got to think of a snappy answer, and I couldn't think of one. So.
Well, John,
And it might do it.
it was an extreme pleasure to talk to you. Thank you so much for this conversation.
Well, thank you very much for inviting me. It's been very stimulating.
This was a conversation with John Lane Bell. Thanks for listening and thanks for being with us. I hope you have enjoyed this conversation. This was Back to the Stone Age.